System 7 using properties exponents. Learning target 2, part 2. So we're still in the same learning target, but this time we're going to look at simplifying expressions by looking at the zero property. So for example, if we had x to the 0 power, y to the 0 power, what that would be simplified to. And our other one is going to be a power property. So if we have x to the 2nd power and then to the 4th power, that's why we call it power property, because there's two powers going on here, what would that simplify to? So let's get started with the zero exponent rule. So for example, we'll just get started right away into some examples. Let's say we do have 5 to the 0 power. So I'm going to show you the pattern in which we get this value, and then I'm going to show you how this always happens. So we're going to start with like this pattern of 5 to the 2nd power, which is 25, because 5 times 5 is 25. 5 to the 1st power is 5. And I'm actually going to go back. Let's go 5 to the 3rd power. It's 125. So 5 to the 3rd power is 125, 5 to the 2nd power is 25, 5 to the 1st power is 5. So if you notice a pattern, and we kind of look like at this in learning target number 1, that we're always dividing by 5 as we are decreasing in powers. So if that pattern continues and we divide by 5 again, 5 divided by 5 is 1. And if we look at our pattern over here, power of 3, 2, 1, this would have to be the power of 0. So notice that the power of 0, or 5 to the 0 power, is 1. Let's look at another pattern just to make sure. Let's go 4 to the 3rd power, 4 to the 2nd power, 4 to the 1st power, then 4 to that 0 power. So just decreasing those powers by 1. And so 4 to the 3rd power, so 4 times 4, which is 16 times 4, is 64. 4 times 4 is 16. 4 to the 1st is 4. So if we're looking at our pattern, we're dividing by 4. We're dividing by 4. 16 divided by 4 is 4. And so if we divide by 4 again, so 4 divided by 4, notice we get, again, 1. So we could do this for many examples if it has the same base, and we could follow that pattern that we learned in Learning Target 1. And we're going to notice that anything to the 0 power is always equivalent to 1. So that doesn't change idea if we change these to exponents, or I'm sorry, to variables. So x to the 0 power is 1. X to the 0 power, y to the 0 power is 1. So anytime you get a value of any type of base to the power of 0, the outcome is going to be 1. In this case, if we go back to this one, just to make sure you understand, this is 1, this is 1, so that's why 1 times 1 gets back to 1. So let's look at one more example. Let's go 8 x to the 7th power, y to the 0 power, times x to the 1st power. So if we look at this goes back into the property, or the multiplication product rule, and we're just going to multiply. So as I've said before, you're just going to multiply the coefficients, and there's not a coefficient here, but we know mathematically that could be 1. So 8 times 1 is 8, and the exponents we add, so we have x to the 7th power plus x to the 1st power equals x to the 8th power, and here comes that 0 exponent rule, and we have y to the 0 power, and we know that value is 1 now. So if we could put a 1 here, we're going to multiply it times 1, but we want it simplified, and so if we think mathematically, 1 times 8 times x to the 8th power really just turns into 8x to the 8th power. So if we look down here, just to make sure everybody is clear on this, the 0 property rule, if 0 is in the exponent, then we are concluding that that is equal to 1. Power rule. So the power rule is kind of like I explained. It's a power to another power. So let's start with, let's go 2 to the third power to the fourth power. And we're not going to actually get a value of this. We're just going to simplify it, and then we'll put variables in it so we can look at it with variables. So 2 to the third power. So this part of the power right here, we've looked at before, and that's 2 times 2 times 2. And now if I put this power back over to the fourth power, so we have 2 times 2 times 2, because 2 to the third power is equivalent to that. We've left the power of 4 on the outside because we haven't taken care of that. So if we think about that, that means there's 4 2 times 2 times 2. So if I were to write that all out, here's 1 power. Here's to the second power, to the third power, oops, and finally to the fourth power. So if I'm going to simplify this, I would count up how many 2's are, because notice it's just multiplication. You go back to that product rule that we looked at in the video before, and we would just add up all the 2's here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is 2 to the 12th power. Let's look at it with an exponent. Let's say it is x to the second power to the fifth power. Okay, so you could, and I'll show you both ways here. We'll just do it the same way I just did it. So you could write out what's inside, which is x times x, because there's x squared, so 2x's, and then to the fifth power. That means I'm going to write out x times x 5 times. So x times x, x times x, x times x, and one more. So we have fifth power, just make sure 1, 2, 3, 4, and the fifth. So then I'm just going to count up the x's here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So x to the 10th. So x to the second power to the power of 5 is x to the 10th power. So hopefully you're starting to notice a pattern here that will make this simpler for us to figure out. I'm going to erase these so I can get some more examples. Okay, so let's go with x to the fourth power to the sixth power. Another way you could write this, and if you'd rather deal with the outside power first, this means there's 6x to the fourth powers. So it doesn't matter if you do the inside power or the outside power first. I'll just show you another technique you could write. So since there's 6 of these, I could write them out like so. So 1, 2, 3, 4, 5, one more, and 6. Okay, so now I have 6x to the fourth, and if I wanted, I could simplify this even more down into x times x times x times x, and then x times x times x times x, and I could do that for all 6 powers. But I'm starting to notice a pattern here. If I write these all out, these are 4x's here, 4x's here, 4x's here. So I'll notice that if I wanted to, I could think about this as addition. So this could be 4 plus 4 plus 4 plus 4 plus 4 plus 4. But I can also know that a repeated addition is just multiplication. So this is technically 4 times 6 powers. So 4 times 6 powers would equal x to the 24th, because 4 times 6 powers is 24. Another example. Let's throw a coefficient in front of there. Let's say it's 2 to the x to the 5th power, and we'll put another variable in there, y to the 8th power. Well, I'll have that to the power of 2. So when I look at this, and it might be simpler when you first start doing these, is to kind of divide this down into one problem at a time. So what I'm talking about is if I just take each one of these exponents, or in the first case, it would be a coefficient, and just put it to that second power. So this would be 2 to this, well, this actually to the first power squared. And this would be x to the 5th power to the second power. And this would be y to the 8th power to that second power. This way, then I'm not looking at so many as a big problem. I can look at it simpler, more problems. So I'm going to start with the coefficient here. And again, as I've taught you before, if it's a coefficient, just treat it like a coefficient. Don't do anything fancy. Don't do a rule to it. Just treat it like that coefficient. So 2 to the second power, if I ignore this 1 that I just put there, is technically it's there, but mathematically we don't acknowledge it when it's to the first power. And 2 to the second power is 4. So my coefficient is 4. Now over here, I'm going to go into that same rule, that power rule that we just talked about. And if I think through this, if this is 5x's, and then I'd write it out twice, that means there's 10x's. Or if I think about if I write it out 2 times, 5x is 2 times, so x times x times x times x times x, and do it again, x times x times x times x times x, I will notice there are 10x's. Y would be my next variable. So I have 8y's and 2 powers of those. So 2 powers of 8 would make 16y's. So this would be 4x to the 10th, y to the 16th. Okay, a couple more examples, and then we'll finish up with the rule. So let's go with, we'll do one more like that one. Let's go 6x to the 7th, y to the 2nd, all to the power of 10. Okay, so we're going to treat coefficients like coefficients, and I'm just going to divide this up so we can kind of see this better. So this would be 6 to the 10th power, which is going to be a very large number. We'll have to put in our calculator here. X to the 7th, then to the 10th. Put that in parentheses. And then y to the 2nd power, and then to the 10th power. So I'm going to grab my calculator here. And on the test, I will not have an exponent this large. So it'd be 6 to the 10th power, and that value is 604661676. I'll put my commas in there to make it an actual problem, a number. So I get 60,466,176. So that is a large number. And again, we won't do that to you on the test. And then we're going to go into our x's here. So there's 10 groups of 7x's, so that would be 70x's. And this last one, there are 10 groups of 2y's, so that would make 20y's. So notice I keep just multiplying the 2 powers. That makes my problem a lot simpler. I could write it all out, but my goal is to make it efficient and simple for me. One last example. So I want always positive exponents. So let's say we have 2 to the x to the negative first power, y to the third power, and then all this to the power of 4. Okay, so simplify it by writing them out separately. So 2 to the 4th power, x to the negative first to the 4th power. Notice I keep giving that 4th power to every single thing in here because every power or every exponent is to that power of 4 too. Y to the 3rd power, and then to the 4th power. So let's deal with my coefficient. So 2 to the 4th power, so 2 times 2 is 4, times 2 is 8, times 2 is 16. So this would be equivalent to 16. And I know this would be weird to write out, but this means there's 4 groups of x to the negative 4th power. So that would be x to the negative 4th power. And the last one here, we have 4y to the 3rd powers. So 4y times y times y, and that would be just 4 groups. That'd be multiplication, so y to the 12th power. But in the test or on our packet practice, we want it with a positive exponent. And so the only thing that doesn't have a positive exponent right now is x to the 4th. So remember from the previous video, if it has a negative exponent, we're going to drop that into the denominator, and we're going to put 1 on the top in the numerator. So that would look like 16 would be at the top here, and then x to the 4th power would go down into the denominator because I'm going to put that over 1. And then y to the 12th power is still at top. So if I mathematically simplify this, 16 times 1 is 16. So I'm going to end up putting 16 on the top, y to the 12th, and then all over x to the 4th. And I can look at that one more way, just maybe more visual for you. This would be 16 times 1 over x to the 4th times y to the 12th power. And notice that if I want to write these as ratios or fractions, if I look at the top here and you're multiplying fractions, you're going to take 16 times 1 times y to the 12th is where I got that value. And 1 times x to the 4th times 1 again is where I got x to the 4th. So just a reminder from the first video of what to do with if there is a negative exponent. So to finish up right here, we're going to look at this last rule. And if you are raising an exponent to another exponent, which is a power rule, you are going to multiply the exponents. So it's like repeated addition. You're just going to multiply those exponents. So such as if we go back really quickly here, just this problem is x to the 3rd power to the 4th power. There's 4 groups of 3 y's. So that is 12, or we can take 3 plus 3 plus 3 plus 3, and notice that's 12. So again, when you're raising an exponent to another exponent, or the power rule, you are going to multiply the exponents.